Okay, everybody. So what I want to cover now is just the concepts of comparing sorting algorithms and their running time. So usually we have three scenarios that we need to look at. The worst case, or what is the largest number of operations an algorithm must do in order for it to um, be done. The best case, which is the smallest number of operations that could be done, and then usually the average case, or how many operations will the algorithm take on average to complete it. Average case is usually the hardest to determine. These ones are pretty easy using the concepts of time complexity. And what we could do here is this concept of experimental analysis where we run different sorting algorithms and then see what happens. So what I want to do here is inside of your selection sort.py file, there's a file called time sort or a function called time sort. And what it takes in is it takes in a sorting algorithm that are given up here and an n. An n is going to go ahead and determine how big of items we're going to use, and it's going to pass this n to this generator list, which is going to just generate a bunch of random numbers for us to use. Now, what we could say here is I'm going to go ahead and try to use selection sort on a list of 0. We'll see here we'll go to 0, and then if I get a 10, it's not too bad. So it's taking 0.0 seconds to sort items of a 10. If I do 100, it's still at 0. What happens if I go up to 1,000? Well, notice that it's actually increasing a little bit in time. And if I go ahead and try to increase this to 10K, we'll see that I get a little bit of hang time here. And it's taking around 2.9 seconds. And what happens if I go ahead and put it to 100K? You'll notice that it's giving us even more hang time. And it's in general, because time sort of selection, or excuse me, because selection sort is is a quadratically timed algorithm, it's going to take a lot more time to sort these larger lists of items than the other ones. So what we can say here is that selection sort runs in quadratic time or n squared time. So based on the size of n, we're going to have n squared runtime. Now, let's go ahead and I'm going to hit Control C to cancel this because it's going to take too long. What if we go ahead and try to use merge sort on this exact same list? So I'm going to go ahead and say, you know what? I'm going to use merge sort here. And we'll see here, this is where the logarithmic end time comes into play. Merge sort almost happened instantaneously in comparison to time sort. And let's go ahead, or excuse me, in comparison to selection sort. Merge sort isn't invulnerable. You'll see here that this actually takes around 4 seconds as well to run. But you can kind of see that there's a comparison that based on the size of n, you're going to get a certain runtime average, or like in the best case scenario. And these are all randomized, like a truly pseudo-random item. So we're going to get different values outputted. But in general, this is going to be a logarithmically running timed algorithm. So we're going to take the log of n, and that's in general how long it would take to run that algorithm. So again, this is a main difference between what we see with sorting algorithms as selection sort. And to reinforce our sorting algorithm concept, an n squared algorithm takes around this long. Let's go ahead and try. This one isn't inside of the notes that's given to you, but it is here that we put together. We'll see that insertion sort also takes the same amount of time to sort a list too. And insertion sort, if you see here, has 2 loops, so it is going to take n squared amount of time. Great. One more thing that I want to take a look at is this compare fib.py file. There's 2 of them in here. I believe the compare fib is empty for you to go ahead and take a look at if you want to try to input this. If you take a look at the other file, compare fib in class, that is going to go ahead and take a look at the solved version of it. What we're doing here is we're just taking a look at the iterative Fibonacci sequence and the recursive Fibonacci sequence. So what I'm going to do here is I'm going to take the timing curve, and I'm going to go ahead and try to run this guy. And we'll see here that as I increase my problem size up until around 32, I believe, it's going to keep increasing the amount of time it's taking. We're going to see here it's actually taking quite a bit of time after 32. And what we could do now, instead of doing recursive Fibonacci, I can do iterative Fibonacci. And we'll see here that this one's almost instantaneous. So this is an issue that comes into CS as well, is where there's not a single catch-all answer to your questions, right? Recursion works really well with merge sort, but recursion doesn't work really well with the Fibonacci sequence. Iteration works really well with the Fibonacci sequence, but if we look at, back into our selection sort, we remember that selection sort, which is iterative, is horrible for sorting. So again, you kind of have to pick your battles with these, and these comparison timing mechanisms and evaluative analyses are how we're going to do them. So again, in general, I just wanted everyone to be exposed to these concepts of runtime and how you can go ahead and use these sorting algorithms. They're not too important for the end of this course. There will be some questions on it for the extra credit, just general basic questions to help prep you for the later courses. So please make sure you review a bit of these if you did want to do the extra credit. And again, play around a bit with these experiments and definitely take a look at the chart here. There's a website called Know Thy Algorithms. Oh, I can't find it. It's not a sound. There we go. Oh, excuse me, not algorithms, complexities. And we can see here that this is the complexity chart that we are going to look at. And we'll see that the log n is down here at the bottom. And we could say merge sort is around, actually, merge sort is more so here in the n log n. And we can see here that linear, so from a for loop is linear, we go from 0 to n, is going to increase steady linear pace. Look at n squared right here. We'll see that it increases probably like really horribly right away. And that's why our selection sort has such a bad runtime when it's running. N log n is a really good sweet spot for some algorithms, but usually you want to be in these areas here. Whereas over here, no one is ever going to hire you if you try to make algorithms that run in that time complexity. So for nested for loops are good for the problems that we did before, but going forward, you're going to want to try to unlearn them as well.